Everyone, so this is going to be module 13C. It's not in the textbook, unfortunately, because this is going to focus on doing the analog to digital conversion on your FPGA, which is going to be the BASIS 3 board that we have in the lab. Okay, and I'm also going to take advantage of this lab, which is going to be most likely for at least the current semester's offer. Is going to be the last lab to show you guys how to use the IP catalog. IP means intellectual property. So these are circuits that other people have developed, and then you can download them and use them for free for some of them, but some of them you have to pay for. And I'll also show you how we can interface with this with the computer. That way you can actually save the data from your FPGA so you don't have to like write down a bunch of numbers to plot them. Okay. So the idea is that while doing ADC or DAC on a breadboard, allows you to create the electronics, right? But you can also interface this with a computer, and that way the computer actually gets the data and record it. And when you have computer interfacing, it allows you to do more complex analysis on the data when you're not taking data. So it's you can run things offline, right? That's what it's called. Okay. So the digital output that's made by the ADC 0805, which is the chip we were talking about previously, you can literally plug that into a computer. Use if you have it has a parallel port, or you have to go through a parallel to USB converter, or some computer even has these general purpose input outputs, and that way you can actually interface with that. And these things are actually not a lot on consumer computers. These are if you want to use a Raspberry Pi with it, and these will have like these general input and output with it. And that's actually how we used to run the lab before we switch it over to the FPGA. Okay. So one thing we need to note when we're doing ADCs on your FPGA is that the BASIS board, instead of using TTL logic, it uses CMOS logic, which actually digital 1 means 3.3 volts, not 5 volts. Okay, so we're going to have to be very careful about selecting the voltage to make sure that you can actually you're not mixing up these two different voltages, because if you apply 5 volts to a 3.3 volts interface, you're just going to burn that interface and it's just going to break, and then now you don't have a BASIS board anymore. And then the department's low 1, and I'm not sure what's going to happen, how we're going to get that replaced from, right? But the BASIS board has an ADC input, so it has one of the PMODs over here, or the one on the lower left, is actually an ADC input. So you can program that to do the analog to digital conversion for you. Okay, that's where it's located. The way we're going to do this is by showing you how we can actually use, well, technically what you can do is you can write your own code, write your own ADC to create all the successive approximation ADC in order for you to convert that. Okay, and this particular the ADC that's on the BASIS board is a 12-bit ADC, so it has 2 to the 12 levels, whatever that number is. That's 4,000, yeah, about 4,000. And it can do 1,000,000 conversions per second. Okay, so remember back when we were talking about the ADC 0805, which is the chip we have, right? That can do 10,000. Okay, so this is going to be 100 times faster than the ADC chip that we have. Okay, so which is nice. But in order to use this, what we're going to do is we're going to show you how to use the IP catalog, meaning we're going to just take someone else's circuit and use it. Okay, and this is the cool thing about Vivado and Quattrus if you're using the Intel version of this, because you can share your circuits and even like patent it, and then you can actually sell it. Okay, The way you do this is you go through this thing called the IP catalog, which is something you've probably seen on the screen, but you just never click on it. Hopefully you never clicked on it. These are modules that's been written by other people, right? Who maybe, probably more expert than us. Some of them are free, some of them cost per use. So it's kind of like a little app store for an FPGA. Okay. So when you click on the IP catalog, what you're going to see is this big list of stuff, right? These are organized by categories, right? So what we're going to do is we're going to search for XADC, which is what's on the BASIS board. Okay. If you search for XADC, hopefully this wizard of XADC wizard pops up. It uses an XE4 interface. Don't worry too much about that. But this is the license for this is free if you're using this from the United States. So when you double click on this, what happens is that this little wizard comes up, and the cool thing is that it kind of have a bunch of visualization that you can use. So these are the inputs that you can give it, and then you have a bunch of different outputs, and then these are actually the analog output, the digital outputs that can actually give you. But okay, so this is like set to 5 bits for some reason right now. Well, this is the channel, not the analog, not the digital output. So it actually can do 5 different channels at the same time. Okay. But what we're going to do is we're going to just use a single channel, okay? Because we're only going to do one at a time. You can actually set the conversion rate. So right now it's set to, so this is 1,000 kilo samples per second. So SPS means samples per second, and it's kilo already. So this is actually set as its maximum speed, which is going to be 1 million samples per second. Okay. Notice that the clock frequency runs at 100 megahertz. So notice that, it takes a little bit of time. So this takes 100 clock cycle in order to do one conversion. What else is there? There's a lot of defaults here. The lab tells you like which one to set in order to get things to work. But it's doing a single channel 12-bit, which gives you about 4,000 analog levels. Okay. Once you finish that, you customize. Once you customize the IP, what's going to happen is that it's going to generate the code for you. Okay. And this code is going to live in this XADC wizard. And what we're going to do is we're going to actually, we don't even get to see the actual Verilog code. What they show you is these .veo file, which is basically how you would instantiate it. You get to instantiate it, but you never actually get to see the inside the module themselves. Okay, so this is just a little template to instantiate it. And if you open this, you're going to see this big old list of stuff. Okay, don't be scared by this. We'll go through this. In the lab, you go through this one by one. Okay. And you just have to customize it for what we need for our lab. So this EOC N of conversion output, right? We can put that as an output for one of our LED. That way, when the conversion is done, that lights up. When the conversion is not done, it's off, right? And then you have your DO, digital output out, right? So this is a 16. Is a 12-bit converter, but we're going to put in a 16-bit output there. Okay. And then these are the inputs that we're dealing with: the JXADC 0 and 1. So this is the negative this is the positive input for the analog. Right, these are the analog output. Right, this is the negative. So we're just going to treat this as ground, and then this is whatever your signal is going to be. And there's a bunch of other settings here. This hex display is not relevant here, but what this allows you to do is someone else's module that's already written. All you have to do is instantiate it, okay, and then you have an ADC that's going to be working. So it gives you digital bits if you give it analog bits, analog information. Okay. But what we want to do next is to be able to record this information The FPGA, as you can see, doesn't, it has its internal memory, but there's no screen for you to read it, right? Well, actually, there's this, the numbers, you can read it, but you want to transfer this so you can write it out as a file so that you can actually use this data in the future, right? This is where computer interfacing is useful. We're going to use UART. This is Universal Asynchronous Receiver Transmitter. Okay. If you ever play with the Arduino, this is basically a communication protocol. It uses this through UART. It's slow, but it's good enough for us to work. Okay. And it can run at different baud rate. So if you ever know, what baud rate is, it's just basically how many bits per second that it can send. And I think the lab just tells you to use the lowest one because we don't really need the data to be that fast anyway. Okay. The way this works is that UART has a little packet. Okay. The start of the data is it's just 1 bit. And then what happens is that it sends, let's say, 5 to 9, that's 5 bits of data, but usually you send more than that. That'll allow you to check this is the data packet itself. And then you also have some parity check, whether or not the data should multiply up to an odd or even number. That's just, give you a 50-50 chance that your data is sent correctly. And then you also have some stop bits. And then this data, right, I'll show you, this is 5 bits. And actually it doesn't say where it is. Okay. But there's a setting that allows you to send how many bits per packet. That's going to be important because the number of bits that the computer is expecting has to match what you are sending it. Otherwise, it will just wait forever. Okay. So once again, we're not going to write our own module in order to do this UART, right? We're going to use the IP catalog, okay? And the way we can do this is just using a more general purpose microcontroller. It's called MCS, okay? It's called Microplace MCS. It's a microcontroller that allows you to control the flow of inputs and output between your FPGA and your computer. Okay. And then you go through the same exercise where you customize this IP, and then so that way you get to the .veo file, right? So once again, you don't get to see the code, but you get to see the instantiation example. Okay. And then when you have that, what you do is then you put in the information that you need in the template, and then but basically what you do is you create the firmware, the bit stream for it. Okay. But there's one more thing, okay? Because, right, in order for it to write to a file, right, it has to have a computer program that runs in it, okay? So this is where the Bravado SDK, the software development kit, is going to be used in order for you to run a little tiny program that basically writes the information out to a file, okay? All right, and this is done by first exporting the hardware, meaning basically you have a description of your ADC and your UART, so it's sending out the data, right? These ones and zeros, okay? And that way, the whatever program you're writing is going to be written on top of that in order for it to grab the outright outputs in order to write it to a file system that's going to be on your computer, okay? So when you launch this SDK, well, once you have to export the hardware first, okay? What happened is that when the hardware is exported, it'll show up as a HW platform, and then they go through this lab, and then and it's going to give you, whatever your top module is called. It may not be called top module, okay? What happened is that this will have this microblaze. Yeah, there it is. And these are going to be the memory addresses that's going to be used in order to share memory between your software and your hardware. Okay. And then I think this lecture kind of goes through like, oh, you want to create this an application out of it because we want to run a program, right? That's on that's built on top of that hardware. Okay, okay, and this little microblade processor allows us to run a little bit, of software. Um, so what you do next is you go through this creating this application. You're gonna just follow the lab manual, and what happens at the end of this is it's gonna create this file called Hello World. Okay, which is typically how a lot of programmers learn how to write their first program. You just type in echo hello world, whatever it was that you're using. We're going to edit this file so that it actually saves the data in the right place, in the right format. Wait, what happened? Why does it do that? Control Z. Okay. And then, so this is not a programming class, so I don't expect you guys to know how to write these code yourself. So I'll just provide the hello world file for you. All you have to do is just copy and paste it over. Okay. It's actually on the thumb drive. Once you created this hello world file, what you want to do is generate this thing called an ELF file. This is called an executable linkable file, meaning it's a file that's executable, but you have to link it to your FPGA hardware. Okay. These ELF files, right? Once your compilation is correct, you see this message down on the bottom, right? Then what you want to do is actually save that, and then once you save that, you're gonna go back to Vivado. So the SDK is a separate program. It's a software interface program, where Vivado is the hardware. Okay, and then you go back to Vivado, and then you associate this ELF file into your FPGA. So basically, what happens is that it links it onto the FPGA. So when you program the FPGA, it sends that program into there also, and then it runs automatically. Okay. And once the device is programmed, there's a little terminal. It's not a great interface, but it allows you to connect to the device through a COM port, which is what the UART uses. And then you should just get numbers that's popping out as the ADC is running. Okay, so we'll test this at low speed at first, and then you'll get to get faster and faster, and then see how fast you can push the ADC converter on your fastest port. Okay, so that's the description of how you do ADC on your FPGAs. Mostly doing it by using this IP catalog, but I think this is a useful thing because a lot of times you end up not writing your own module because someone else has wrote it, right? So um, why write it yourself? And especially since a lot of times the ones that are shared are much more well refined. Okay. All right. So that's all for module 13. So I will see you guys in class.